Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we are going to be discussing thermal expansion. And take note, this is under thermodynamics. So relax, do not go anywhere and we'll be right back. You are welcome back to my school YouTube channel. Like I said earlier on, we are going to be discussing about thermal expansion, and this comes under the main topic, thermodynamics. So before we begin with our lesson, let's quickly run through the objective for today's lesson. So objective number one, at the end of this lesson, you should be able to define thermal expansion. 2, explain the types of thermal expansion. 3, solve simple problems involving linear, area, and volume expansivity. 4, explain expansion in liquid. 5, explain the anomalous expansion of water. And 6, explain the consequences and application of expansion. So let's begin with our lesson. So most solids expand when heated, and the rate of expansion varies from one solid to another. And the expansion is more pronounced in gases, followed by liquid, and least in solid. A substance, whether solid, liquid, or gaseous, consists of molecules. When the molecules is heated, the molecules gain kinetic energy and move faster, and hence the molecules take up more space in the substance. This leads to expansion. Therefore, we define thermal expansion of a solid as the tendency of the solid, in this case matter, to change in shape, area, and volume in response to a change in temperature through heat transfer. So thermal expansion of solids can be further classified into 3 types based on the change in dimension. So the first type, we have the one we call linear expansion. Okay, so linear expansion is expansion in length of an object. Linear expansion is expansion in length of an object. Different objects expand at different rates. For example, when steel and iron are heated under the same condition, okay, steel expands more than iron, and the reason for that is because both of them have different coefficient of linear expansion. Okay, so what I'm saying in essence is that the expansion of a material, okay, of a solid, depends on the coefficient of linear expansivity of that material. Okay, so let's move to the next slide so that we define what we mean by coefficient of linear expansivity. Now take note that the coefficient of linear expansivity is denoted with alpha. Okay, so this symbol is called alpha. Okay, and it is defined as the increase in length per unit length by degree rise in temperature. Okay, and the unit is per Kelvin. Okay, the unit of coefficient of linear expansivity is per Kelvin. So mathematically, alpha, which is coefficient of linear expansivity, is equals to change in length, okay, divided by original length times temperature rise. Okay, so this temperature rise is also known as change in length, right? Now take note, this change in length is, you can especially call it increase in length, okay, or increase or expansion, right? So this is given as delta L, okay, delta L all over L1, which stands for the original length, times delta theta, okay, which is equals to, of course, the increase in length is given as L2 minus L1 all over, then the change in theta, okay, or delta theta is given as theta 2 minus theta 1. Okay, so let's interpret all this one after the other. So L2 minus L1 is equal to increase in length or expansion. Why? Theta 2 minus theta 1 is equal to temperature rise or increase in temperature. Okay, so theta 2 is the final temperature, theta 1 is the initial temperature, L2 is the new length, and L1 is the original length. So now that we have covered one type of thermal expansion, okay, so let's solve some example to drive home what we just learned. Okay, so number 1, what is meant by the statement the linear expansivity of copper is 0.000017 per Kelvin? So what this statement means is that the increase in length per unit length per degree rise in temperature of copper is 0.00017 meter. Okay, what this statement means is that the increase in length per unit length per degree rise in temperature of copper is 0.000017 meter. Okay, so that is just the meaning of this statement. So let's move to the next slide so that we continue with the second example. So the second example, we have to move over to the board to solve this because it's a solving question. So, and it goes, a metal rod of length 50 centimeter is heated from 40 degrees Celsius to 80 degrees Celsius. If the linear expansivity of the material is alpha, calculate the increase in length of the rod in meters in terms of alpha. So let's move over to the board to solve this. Okay, now remember that linear expansivity is denoted by alpha. Okay, and the formula for calculating linear expansivity, which is alpha, is equals to the increase in length, right, all over original length times the change in temperature, which is denoted by theta. Okay, now in this question we are asked to calculate the increase in length of the rod, and we must do that in meters. Okay, where we are told that alpha, which is the linear expansivity, alpha is equals to alpha. You can come to the question, right? Now L1 is equals to 50 centimeter, but since we are asked to calculate this in meter, that means we have to convert this to meter. Okay, but remember that 1 meter is equals to 100 centimeters. So in that case, we are going to be dividing 50. Okay, we're going to be dividing 50 by 100 in order for us to get the value of 50 centimeter in meters. So if we divide this, it will be equals to 0.5 meter. Okay, which is 1, 2, which will give us 0.5 meter. So that means 50 centimeter in meter is equals to 0.5. Okay, meters, right? So we are asked to calculate this. So we simply make the increase in length the change of subject of formula. So that increase in length will be equals to alpha times original length times the change in temperature, right? Now we are told that alpha, which is the linear expansivity of the material, is alpha. So our alphas remain because our answer is going to be in terms of alpha. Okay, times 0.5, then times the change in temperature, right? So the change in temperature is 80 minus 40. Now take note, this is the final temperature, while this is the initial temperature. So that we'll be having alpha times, of course, 0.5 is the same thing as 1 over 2. Okay, so let's just do that to make our multiplication easier for us. Then times, if we subtract this, that will be equals to 40, right? So 2 here is 1. 2 here is 20. So that at the end of the day, we'll now be having our increase in length to be equals to 20 alpha meters. Okay, since we are asked to leave the increase in length, okay, in terms of pi and in meter. Okay, so let's move over to the screen to continue with our lesson. So now let's move to the second type of thermal expansion of solid, and the second type is called area or superficial expansion. Area or superficial expansion. So area or superficial expansion is when the expansion of a solid occurs along 2 dimensions. For example, in the case of expansion of a lamina. So a lamina is just a thin material, okay, like paper or metal. Okay, so in case of a expansion of lamina, both length and breadth will expand when heated. Okay, such expansion is known as superficial expansion. Okay, so what is area or superficial expansivity? So area or superficial expansivity is denoted by beta. Okay, it's denoted by beta, and it is defined as the increase in area per unit area per degree rise in temperature. Okay, so mathematically, superficial or area expansivity is given as increase in area all over original area times temperature rise. Okay, so the increase in area is given as A2 minus A1. Okay, while the temperature rise is given as the temperature rise, which is change in temperature, is given as theta 2 minus theta 1. So remember that A2 minus A1 represent the increase in area or expansion, while theta 2 minus theta 1 is temperature rise or increase in temperature. Okay, so let's move to the next slide. So Theta 2 is the final temperature, theta 1 is the initial temperature, A2 is the new area, and A1 is the original area. It is good to note the relationship between linear expansivity and superficial or area expansivity. Okay, so the relationship between these two types of expansivity is beta, okay, is equals to 2 alpha, meaning area expansivity is equals to 2 linear expansivity. Okay, so here are some examples to put these formulas into work. So the first one is the linear expansivity of a material is 15 times 10 raised to power minus 5 per Kelvin. If the initial area is 25 meters square, calculate the increase in area if it is heated through 40 degrees Celsius. Okay, so let's move over to the board to solve this problem. Okay, so let's begin. Now remember, it's important to write out the parameters that are given us first before solving any problem. Okay, so remember that beta, which stands for area expansivity, is equals to change in area, okay, all over original area, then times the change in temperature or temperature rise. Okay, but remember in this question we are given alpha to be equals to 15 times 10 raised to power minus 5 per Kelvin. Okay, and remember that the relationship between area expansivity and linear expansivity is that area expansivity is equals to 2 times linear expansivity. So our beta in this case will be equals to 2 times the value of our linear expansivity, which is 15 times 10 raised to power minus 5. And this will be equal to 30 times 10 raised to power minus 5 per Kelvin. Okay, now the original area was given to us to be equals to 25 meter square, right? Then the temperature rise, okay, which is the change in temperature, was given to us to be equals to 40 degrees Celsius. Okay, so now that we have our parameters, then we just fix them into the formula and get our answer. Now remember, in this question we are asked to calculate the increase in area. So we just make the increase in area in this formula the subject, the subject of formula. So in that case, increase in area will be equals to the beta, okay, times A1, then times the temperature rise. Okay, but remember that our beta, we have already gotten the value to be equals to 30 times 10 raised to power minus 5. So here we fix 30 times 10 raised to power minus 5, then times the area that is given to us, which is equals to 25. Then the temperature rise is given to us in this question to be equals to 40 degrees Celsius. So we have 40 here. So if we multiply these two, we'll be having 30 times 10 raised to power minus 5 times, this is going to give us 1000. Okay, so let's write that in standard form to make it easier for us. So that we'll be having 30 times 10 raised to power minus 5 times 1 times 10 raised to power 3, right? So we'll multiply these two. Okay, let's continue solving here. So we'll multiply 30 and 1, that will still remain 30. So according to the law of indices, we are going to take one of the 10s. Okay, that will give us 10. Then we add the power since we are multiplying, so that will be plus 3, right? So that we'll be having 30 times 10 raised to power minus 2, right? So if we put this, if we change this to ordinary form, of course this is not a standard form anyway, but if we take this to ordinary form, we'll be having 0.3 meters square. Okay, 0.3 meters square, more or less like we have 30, right? And our decimal point is here, so we're moving it twice, so that would be 1, 2. So this will result to 0.3, okay, 0.3, or, okay, let's put the 0, which will give us 0.030 meters square, okay. So this is the answer to example 1 question. And remember, in the example 1, I asked to calculate the increase in area, okay. So the increase in area is equals to 0.30 meter square. Okay, so let's solve the second example. What will be the new area of 400 centimeters square of a solid if its temperature is raised by 10 Kelvin? Now here we are asked to take linear expansivity to be equals to 19 times 10 raised to power minus 6 per Kelvin. Okay, so let's move over to the board to solve this question. So first thing first, let's write out the information that is given to us in the question. So original area, which is A1, in this case equals to 400 centimeters square. So A2, which is the new area, we don't know. Okay, we are given linear expansivity to be equals to 19 times 10 raised to power minus 6 per Kelvin. Okay, but remember that area expansivity is equals to 2 linear expansivity. Okay, so that area expansivity is equals to 2 times 19 times 10 raised to power minus 6, and this will be equals to, if we multiply this, that will be 38, right? 38 times 10 raised to power minus 6 per Kelvin. Okay, but remember that area expansivity is given as increase in area, which is A2 minus A1, okay, over A1 times the temperature rise, right? So in this question we are asked to calculate A2, which is the new area, right? So if we make A2 the subject of formula, we'll be having A2 to be equals to A1 bracket 1 plus beta, okay, times the change in temperature, okay, times the change in temperature. But remember, we've gotten the value of this, so we just substitute the given data into this formula. So A2 is equals to A1 is 400, then bracket open 1 plus, this is already 38 times 10 raised to power minus 6, then times the temperature rise. So in this question, the temperature rise, sorry, I did not write it the first time. So the temperature rise was given to us to be equals to 10 Kelvin, right? So here we put 10. Okay, so if we deal with this, this is 400, then we'll be having 1 plus. Now let's deal with this 10. So this 10 is still the same thing as, say, 1 times 10 raised to power 1, right? So 1 times 38 will still remain 38. Then for these two 10s, we are going to apply the law of indices. So that we'll be having times 10. So that we'll be having times 10 raised to power minus 5. Okay, so 38 times 10 raised to power minus 6 times 10 is going to give us 38 times 10 raised to power minus 5, right? So we can break this down. Let's change this to ordinary number, right? So let's solve it here. So that we'll be having A2 to be equals to 400 still outside, bracket open 1 plus. So we just move this, there's an invisible decimal point here because this is a whole number, so there's an invisible decimal point here, and in that case we are going to move that decimal point 5 times to our left, okay? So that we'll be having 1, 2, right? So that at the end of the day our answer becomes 0.00038, okay? So if we add this, we'll be having 400. If we sum up everything inside the bracket, we'll be having 400 times. Remember that bracket represents times. Okay, so that we'll be having 400 times 1.00038. Okay, so at the end of the day, this will be equals to 400.152. Okay, and our answer should be in centimeter square. Okay, so the value of the new area is equals to 400.152 centimeter square. Okay, so let's move over to the screen to continue with our lesson. Okay, so the answer to this question is 400.152 centimeter square. So let's move to the next slide. So on the next slide, we'll be talking about volumetric expansion or cubical expansion. Okay, so when the expansion of solids occur along 3 dimensions, e.g. in the case of expansion of lamina, both length, height, and breadth will expand when heated. Such expansion is known as volume or cubic expansion. Now, what you must know about lamina. Lamina also has thickness, okay, but it is often considered as 2-dimensional, so just take note of that. So cubic or volume expansivity is represented by gamma. Okay, so this symbol is called gamma, is denoted by gamma, so this is called gamma, and it is defined as the increase in volume per unit volume per degree rise in temperature. So mathematically, volume or cubic expansivity is given as change in volume, which is the same as increase in volume all over original volume times temperature rise, which is, now change in volume is V2 minus V1, okay, over why the temperature rise, just as we have seen earlier, is theta 2 minus theta 1. Okay, so V2 minus V1 is equals to increase in volume or expansion. Theta 2 minus theta 1 is equals to temperature rise or increase in temperature, where theta 2 represents final temperature, theta 1 represents initial temperature, V2 represents the final volume, or you can call it the new volume, while V1 represents the original volume, or you can as well say initial volume. Let's move to the next slide. So it's also important to know that there's a relationship, okay, that exists between linear expansivity and volume or cubic expansivity, and that is cubic expansivity is equals to 3 times linear expansivity. Okay, 1 cubic expansivity is equals to 3 linear expansivity. So this is where we draw the curtain for the preview of today's video. Okay, you can watch the complete video by clicking on the link in the description below, and that will take you to my school website. There you have to subscribe to enjoy the complete video. In the complete video, we did solve some examples under volume expansivity. Right, we also discuss about expansion in liquid. We also talk about anomalous expansion of water and many more. I believe you enjoyed the preview of the video that you have watched. If yes, please hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next video.